has voltage. So that's the E and the V. I is current. And then, how much of it flows? What controls how much of it flows? What keeps it from all flowing out? Resistance, our third thing. So everything has some resistance, something that stops it from happening. In our pipe, going back to our water, the bigger the pipe is, the faster the water will flow. If you make the pipe smaller, the water will flow slower. As you constrict it further and further and further, it'll get down to a drip and down to nothing. And that's increasing the resistance, changing the width of the pipe. In electricity, we have something that's similar that we call resistance. And we use an R. One of the few times we use the right letter. Okay, so then we come up, has anyone ever heard of Ohm's law? Ohm's law, Ohm was a guy who studied this stuff back when no one knew anything about it. And he created a law. And his law is, or one form of it, is E, electromotive force, equals I, current, times resistance. Now there are different forms of that. What happens if we know the current and the resistance? This is how we can figure out what the electromotive force is. If you can also just play around with this arithmetically. So R equals E over I. If we know a voltage between 2 points, and we know how much current is flowing, we can calculate what the resistance of the path is. And then the final one, I, E over R. If we know the voltage across 2 points and the resistance, then we can tell how much current is flowing. So those are the different forms of Ohm's law. Ohm's law is very important because, like I said before, if we didn't have any resistance, what would happen here?
Short circuit.
Short circuit, and the battery would be destroyed.
And the wire would melt.
Well, no, the wire would not melt. That's kind of a true short circuit. The wire will never melt. There's no such thing as a true short circuit. Let's move on to the next equation and show you why. The power law. Now this is very important. Power is also related to these same units. Power, which can also be considered in some cases the amount of heat generated, very important for burning up the wire. Power is equal to the voltage times the current. P equals EI. Okay. Now we can play with this in other ways, just like with this one. Same thing. We can say I, the amount of current that flows, is equal to the power over the voltage. Or we can say that the voltage equals the power over the current. Just playing with that equation. However, you can also play with the two equations and put them together and come up with a whole new set of relationships. Now, why is this important? Because when we want to make things happen, we have to figure out, are we going to burn up the wire when we make this connection? We also need to, in radio especially, the amount of power we use directly affects how far we can talk. So we have to be able to calculate the amount of power that's generated. Okay, so now, if we substitute for E, we'll take this equation and substitute it in there. Now you get IR times I, or I squared R. So now we see that the amount of heat generated in a, say, resistor is directly related to the resistance of the resistor. So if you double the resistance, you double the heat, but it's related to the square of the current. If you double the current, you get 4 times the heat generated. Okay, there's another version of this. Let's substitute for R. Oh no, we don't have an R. This one for I. So P equals EI, and substitute I equals E over R. So we get E times E over R, or E squared over R. So in this case, the power is inversely related to the resistance. The more resistance that you put in, keeping this the same, the more resistance you put in, or if you have the resistance, say, you have the power. I'm sorry, that's not right. You have the resistance, you double the power. If it's an inverse relationship. But there's a square relationship to voltage. So if you want to increase the voltage by 2, or by 4, you only increase the power by 2. So these are the, did I say that? I said that backwards, I'm sorry. You increase the voltage by 2, you double, you quadruple the power. So these relationships are very important for, in the end, making radio waves and making them travel. Now, so far, we're just talking about DC. DC doesn't do much for us with radio because the direct current will not jump into the air and go across the world and let you talk to someone else. So what does that for us? So now we have to get into the concept of alternating current. Now what's the difference? Direct current is always in the same direction, plus to minus. Alternating current actually alternates back and forth. It'll go this way, then that way, then this way, then that way. Now, the advantage of that is, there's many advantages of that. All of our plugs where we get electricity out of the wall are alternating current. There's a reason for that, which we might be able to get to later. But Edison, when he was developing this, he wanted to make everything direct current. He wanted to use generate direct current, and then ship it to people's houses. It didn't work as efficiently as alternating current, so the alternating guys won.
Was it Tesla that came up with the alternating current?
I think I saw his name is going head to head with, I don't know if he came up with it, but he was supporting it. He was trying to get Edison out of the way so that they could make these plants. It has to do with all these equations, in fact, and something you can do with alternating current. I think we're going to get to that on another day. I don't think we do transformers just today, but that's
Well, it traveled more miles with less loss
because
of the AC.
Keep going.
So they were able to produce it
Yeah, but-
cheaper and send it many more miles.
But why did it go more miles with less
Because
loss?
of
Overcome the
the,
resistance.
the AC did it that way. Why, I'm not sure, but.
Okay, well,
but
then
but
let me-
they-
then
That
let
was
me,
why one over the other.
let me give you the reason
High
without,
voltage, low amperage.
yes, let me give you the reason without explaining how transformers work, but it has to do with transformers. Let's say you have a piece of wire, and all wire has resistance. You can't avoid it. You can't
Depending on the
avoid it.
thickness, right?
In space, you can avoid it, but everywhere else, we've got resistance. Has to do with the size. But it's gonna have resistance. Actually, somewhere, I don't have it with me, but I have a table of the amount of resistance for different size wires, 12 gauge, 14 gauge. They'll tell you how much resistance there is. If you take wire or anything down to absolute zero, all resistance disappears, and that's why they would like to do that someday, but they haven't gotten there yet. That's superconducting. You may have heard about that a few years ago. Some scientists claim to have invented superconducting materials. That's what they're for, or that's what they're valuable for. You get a superconducting material, no resistance, you don't lose anything. Then you could use DC to power your home. So let's go back to Ohm's law and the power law. Substitute heat lost for power, okay? And we have a fixed resistance in a piece of wire going down the street. Can't change that except going to bigger wires, and that becomes,
Expensive.
oh, yes, very expensive, and hard to do, and very heavy, and lots of problems. So, if the resistance is fixed, it's not changing, and the power you want to minimize, what do? Well, let's go over to I squared R. These are kind of called I squared R losses, in fact. So let's say you're going to use a certain amount of power in your house. Now, I'm using power two ways, so don't be confused by that. Power is the work, can be the work done by the electricity that you're buying from the company. There's power in the lights, power in the motor, power in your TV. They all use power. That's good power. That's the stuff you want. That's stuff you're paying for. However, there's other power that's lost in heat getting it to you. So if you want to minimize the power lost in heat, one thing you can do is minimize the current that flows through that piece of wire. Now, you, at the other end, you're demanding, I want a certain amount of power, EI. So, if you want 100 watts, the unit of power, or a unit of power is watts. Let's say you want 100 watts. If that power is given to you at 1 volt, that means you're going to have to pull 100 amps. So if you're using 100 watts, and you take that 100 watts at 1 volt, then that means you need 100 amps. By the way, volt named after Voltaire, amps named after Ampere. There's always someone a long time ago that they named it all after. Now, coming back to this equation, if you have 100 amps, and let's say you have a wire which has a resistance of 0.001 ohms. That's omega symbol for ohms. It's very low, it's a million ohm. So that's a nice big piece of wire. And it should be cold too. Colder the better. In winter you do better. Okay, so now the power lost in this piece of wire is I squared R. So it's 100 squared times 0.001. So 100 squared is 10000 times 0.001. So we move the decimal 3, 1, 2, 3, and we lose 10 watts in the piece of wire. That's 10 watts that they generated that they can't charge you for. They don't like doing that. So now let's say that they're able to convert the voltage up to 100 volts. And for you to get your 100 watts, then you only need 1 amp. It's equivalent in the amount of power that you're going to use at the end. So now, same R, so P equals 1 squared times 0.001, which is 1 times 0.001, which is 0.001 watts, or 1 milliwatt. It's a lot less. It's 10,000 times less. Think of how much money the power company will save if they can do this. Well, that's what they did. But they couldn't do it with DC, because if they were to give you too high a voltage in your house, you tend to get electrocuted more often. My choice of voltage isn't good because that's actually what you get. But let's multiply everything by 100. And you'll see that you can't, it's impractical to put such a high voltage in the wall. So they made a standard, it was 120 volts in this country. But if they put 120 volts over the wires with resistance, they'd lose a lot of heat. So what they do is they jack it up to thousands of volts.